All right, let's talk about matrices. Now, when you look at one, you might just see a simple block of numbers, right? But I'm here to tell you there's a hidden structure, a secret language inside. And today, we're going to decode it together.
So is that really all it is? Just a grid? A box to hold some data? That's what it looks like on the surface, for sure, but we are about to go way deeper. Because what if I told you that this grid has secrets baked right into it? That it has these properties of reflection, that it can be broken down into these core fundamental pieces, and that it even has its own undo button? Yeah, that's what we're digging into.
Okay, our first secret starts with something I like to call the matrix mirror test. It's a really simple operation, but it lets us peek into the deep internal symmetry of any matrix.
Now, this test has a formal name, of course, the transpose. All you do is take the rows and turn them into columns. That's it. Imagine drawing a line from the top left corner straight down to the bottom right. That's the main diagonal, and you just flip the whole thing right across that line. It sounds simple, but this little flip is incredibly powerful.
So here's where it gets really interesting. What happens when we compare a matrix to its own reflection? Well, this mirror test reveals two very special, almost perfectly balanced kinds of matrices. On one side, you have your symmetric matrices. You transpose them, you flip them, and nothing changes. It's a perfect mirror image of the original. But on the other side, you have skew-symmetric matrices. When you transpose these, you get the exact negative of what you started with. It's like a perfect anti-image.
Okay, let's look at a real example. See the symmetric one? Look at the numbers that aren't on that main diagonal. You've got a 2 in the first row, second column, and look, there's another 2 in the second row, first column. The 3 is mirrored, the -1 is mirrored. It's just perfect symmetry.
Now, check out the skew-symmetric one. Two things should just jump right out at you. First, that main diagonal, it's all zeros, and it has to be. Think about it. What's the only number that is its own negative? 0. Second, look at those mirrored elements. You have E and negative E, F and negative F, a perfect negative reflection.
So these special matrices are pretty cool. But here is the big secret. They're not just weird little edge cases. They are the fundamental building blocks of every single square matrix in existence.
It all starts with this really elegant piece of logic called Theorem 1. And what it says is, for any square matrix you can dream up, if you add it to its own transpose, the result is guaranteed to be symmetric. And if you subtract its transpose, the result is guaranteed to be skew-symmetric. We can literally create order out of any matrix we find.
And that brings us to the main event, Theorem 2. Honestly, this is one of the coolest ideas in linear algebra. It means you can take any square matrix, no matter how messy or random it looks, and split it cleanly into its pure symmetric part and its pure skew-symmetric part.
So how do we actually do it? Well, it's basically a simple recipe. You take your matrix, A, and its transpose, A'. The symmetric part is just half of their sum. The skew-symmetric part is half of their difference. You add those two new pieces back together, and poof, you get your original matrix right back. You've just deconstructed it.
Okay, so we've figured out how to take a matrix apart. But what if that matrix actually represents an action, a transformation? Can we reverse it? This brings us to our next big secret, the matrix undo button.
Exactly. I mean, think about it. If multiplying by a matrix transforms something, like it rotates an image in a video game, is there another matrix that can just rotate it right back to where it started? The answer is a big yes, and it's called the inverse.
The inverse of a matrix A, which we write as A with a little -1, is its perfect operational twin. When you multiply a matrix by its inverse, doesn't matter which order, you get something called the identity matrix. And the identity matrix is basically the matrix version of the number 1. It cancels out the original operation. It really is the ultimate undo button. So this undo button is obviously super powerful, but how do you find it? Well, there's a really slick, systematic process for doing just that. Here's the trick. You start by setting your matrix A right next to the identity matrix. Then you start applying a series of simple legal moves, things like swapping rows or adding one row to another. Your entire goal is to apply these moves to your matrix A until you've turned it into the identity matrix. And while you're doing all this, the identity matrix you put on the right side has been getting hit with every single same move. By the time you're done, it has magically transformed into the perfect inverse.
So there we have it. We've just pulled back the curtain on 3 of the coolest secrets of matrices. First, the transpose acts like a mirror, showing us a matrice's internal symmetry. Second, every single square matrix can be broken down into the sum of its pure symmetric and skew-symmetric soles. And third, a whole lot of matrices have an inverse, a powerful undo button.
And that kind of leaves us with one last thought. We've been talking about this mathematically, but just think bigger for a second. From unscrambling a secret message to reversing a complex financial error, or even correcting a glitch in a control system, what real-world problems could you solve if you had a totally reliable undo button?